Bam! Mr. Tarrou. In this lesson, we are going to expand our use of the disk method to find volumes of solids. Now, up until now, all of our solids have had cross-sections which were circles. That was created by, we were given a plane region, some kind of intersecting graphs or some vertical and horizontal lines. We identified the plane region and we rotated it around an axis. Well, if you have cross-sections that are just, as long as you know the formula for the area of the cross-sections of whatever the solid is that you're trying to find the volume of, the disk method can be generalized to take care of that and find the solids of any shape. Now, these won't be created by taking a plane region and rotating it around an axis. That's what creates our cross-sections which are in the shape of a circle. But if you look at this formula for finding volume using the disk method, and by the way, our previous example included disk methods and washer methods where we had sort of a cavity in our three-dimensional object we were trying to find the volume of. It says the volume is equal to pi times a definite integral from a to b of r of x squared dx. And you'd be integrating with respect to x when you had a horizontal line which you're rotating your plane region around, and thus you would have those perpendicular or vertical representative rectangles which we would let their widths approach 0 by integrating with respect to x. Well, pi r squared is just the area of a circle. So this is a more specific, this disk method is a more specific idea of what we're going to take a look at today. For cross-sections of area A of x, taken perpendicular to the x-axis, the volume is, and see, we don't see a pi r squared here because we're not just talking about cross-sections which are circles. The definite integral from a to b of a of x dx. So we're slicing here. I have my attempt at drawing a sort of pointy, squarish looking thing on my chalkboard, and I've laid my x and y axis in a normal fashion of horizontal and vertical. We will play with the orientation of the x and y axis sometimes to do our best to get a three-dimensional object drawn on a two-dimensional plane so it looks kind of right. We're slicing it along the x-axis, and thus we're getting these vertical cross-sections, again, that we're going to let the widths of these approach 0. So we're going to integrate, do a definite integration with respect to x. And this cross-section looks like it might be like a square or a rectangle. So the area formula would be some sort of length times width, or if it was a square, it'd be s squared. Now with these cross-sections, with lower and upper limits of x being a and b. Now, our cross-sections for this video, the first example is going to be a rectangle, the next example is going to be a square, and the final example will be the cross-sections will be triangles. But they really could be anything as long as you know the area formula for that cross-section area. If you are going to take cross-sections perpendicular to the y-axis, then you're going to need your function, your area function in terms of y instead of in terms of x. And the volume is equal to the definite integral of c to d, or from c to d, of a of y dy. So we're coming through, we're taking cross-sections perpendicular to the y-axis. That means we have horizontal representative cross-sections that we want to let those widths approach 0, giving us an infinite number of these cross-sections and giving us an approximation of the volume, which is, with the process of the definite integral or first fundamental theorem of calculus, going to be exactly accurate. So how much of a pretty darn good estimate. With our lower y value of c at the bottom of this volume that we're trying, or this three-dimensional solid we're trying to find the volume of, and the upper value, y value of d with that lower and upper limit on our definite integral. All right, let's get on to our first example. Bam! First example, find the volume of the solid whose bases are bounded by the graphs of y equals x plus 4 and y is equal to x squared minus 2, with the cross-section which is a rectangle with a height of 2 perpendicular to the x-axis. Well, if we're talking about, finding volumes of something geometrical, you should be starting off with, well, drawing it. So we've got a line whose y-intercept is 4 and slope is equal to 1. So we've got a y-intercept of 4 and up 1 and over 1. And again, So we have a line that looks something like that. And a parabola which is equal to y is equal to x squared minus 2. Well, if we know our transformations, this is a parabola opening up with the x being squared. It's got a vertical shift down of 2, so the vertex is at 0, negative 2. If we take 1 and plug it in here, let's see, 1 squared is 1, minus 2 is negative 1. So we've got a point here at negative 1, and positive 1, negative 1. And it's doing some kind of thing where it's opening up from here. Now, I don't want to finish that parabola because clearly these two functions are going to intersect. And like our earlier section finding area between graphs, or the area between two graphs, we had to find the intersection point. So we knew, or we can figure out, what's the lower and upper limit of our integration going to be. Now, this is perpendicular to the x-axis, so we're going to be integrating with respect to x. So I can find the x and y coordinates of the intersection points, but really all I need, since we're integrating with respect to x, are the x values where they intersect. So let me get a bigger piece of chalk here. We're going to set the functions equal to each other. So x plus 4 is equal to x squared minus 2. We have a squared and single degree term, so obviously we're going to set this equal to 0. Bringing the x over and the 4 over, we have 0 is equal to x squared minus x minus 6. Get this factored, and we have x minus 3 times x plus 2. Close that parentheses up. And then we're going to set each of these equal to 0 and get x is equal to positive 3 and x is equal to negative 2. So that's as far as the x values are concerned, the intersection points for these two graphs. I guess maybe for graphing purposes, maybe it would be nice to know where they intersect. So let's see here. If x is equal to negative 2, the negative 2 plus 4 is equal to positive 2. See, the intersection is going to be negative 2, 2. And my graph's not perfect, but it's going to look something like this. And at x equals 3, well, 3 plus 4 is equal to 7, so at 3 we're intersecting at 7. And that's a little bit low there, but let's just pretend that's the value of 3, 7. Okay, whoops, sorry about that. Well, that is our plane region. Now, that is the boundary of one of the bases, but as we come through and we take cross-sections perpendicular to the x-axis, it says here that we have cross-sections which are rectangles. And the height of those rectangles are going to be equal to 2. Now, here's where the drawing part gets a little bit tough. I'm going to need to try and create some kind of three-dimensional object off of my drawing here so far. And it's going to need to look like it has a height of 2. These two functions are going to determine how long the rectangles are, but I'm going to try and draw almost like if I took a piece of styrofoam and I cut it in the shape of what's effectively sort of like a parabola and a line that was 2 inches tall. So let's see here. I'm going to come off of here and just make some kind of arbitrary length, which we're going to be saying that is 2 units tall. And I'm going to come off and try and come parallel to that and the same length at each of these corners. And I'm going to come over the top of my problems here, so maybe somewhere around here. Usually lately I've been stopping the video and just making these pictures, but I want you to have some idea of how to draw your own three-dimensional objects. So I drew a decent parabola, a line, and now I'm going to come off again at these key points and try and draw some parallel lines at an angle that they really need to be parallel, and they all need to be the same length. Now, if you can kind of mimic your previous shapes and connect the dots, you will have this three-dimensional object which we are going to try and find the volume of. And let me dot what would be the back of the diagram. I'm trying to make this look like it's coming up and out of the chalkboard. And that means you would not see this line here. There's a guy that does fantastic chalk lines by pushing the chalk and making it dotted. I've done it a couple times and I'm trying to get the master of it. But don't want to do it on this particular diagram. So I'm trying to show, hopefully see that parabola in that line. It's kind of coming up out of the chalkboard, and these heights are going to be a width of 2. Now thinking about this cross section that we're using to find the volume of this object, maybe we have a cross section here coming through again perpendicular to the x-axis. So that's at the top of the object, so that's going to be solid. Again, trying to keep these lines parallel as much as I can, drawing freehand. Well, that's not the best. This is why sometimes I stop the video and do this off-camera freehand, which I will have to do on the next diagram because it's a bit more complicated. Okay, I hope you can see that. Anyway, we need to get back to the math. We have parabola line, 2 units, 2 inches, 2 feet, 2 whatever units tall. And we have this, what I'm trying to show is a cross section here. I'm going to pull this out and emphasize again that we have this rectangle whose this height right here will be right there. That height right there is a width of 2 or a height of 2, however you want to say it. And then the length of these rectangles are going to be defined by the distance between those 2 functions. Well, when we found area between 2 curves on a plane region, 2-dimensional, we had to take the greater. Now remember, we're integrating with respect to x, so we're looking for x's and then getting from that y values, and we took the greater y value and subtracted the lower y value. So the line is the greater function, so this length is going to be x plus 4 minus the y value that we're getting from the parabola that is below the line, and that is going to give us a y value of x squared minus 2. Now I'm getting to be a bit of a mess, and I do want to pause the video and clean all this up and set up an integral, which is going to be from -2 to 3, and that a of x is going to be, well, our length times our width. Alrighty, now that we have that cleaned up, and I have also cleaned up this function describing the length of the rectangle, distributing this x through and combining like terms, we have -x squared plus x plus 6. So we have the length of the rectangle, the width of the rectangle, we have this definite integral set up. Let's find the volume. This is going to be equal to the definite integral of -2. You can bring this 2 out front since it's just a constant being multiplied to this polynomial, or you can distribute it, which I think I'm going to do. So we have -2x squared, let's not forget our lower and upper limits, plus 2x plus 12 dx. Now we can go ahead and do that integration step. And that is going to come out to bringing this power up by 1 and dividing. We have -2/3 x cubed plus, bringing that power up by 1 and dividing. 2 divided by 2 is 1x squared plus 12x. Again, that lower and upper limit of 3 and -2 that we found earlier. Again, the x-coordinates, where those functions intersected, and why are we using the x-coordinates? Because we are cutting this perpendicular to the x-axis, thus integrating with respect to x. All right, now plugging this in, we have, with the upper limit, -2/3 times 3 cubed plus 2 squared plus 12 times 2. Where's that sneaking in from? That should be 3. All right, plus 12 times 3 minus, now bringing in a parentheses as we introduce our lower limit, so we remember to distribute that if we need to, which we will with subtraction. -2/3 times -2 cubed plus -2 squared plus 12 times -2. And cleaning all that up, and off the top of my head, that volume is going to come out to be, let's make sure I didn't write anything incorrectly here. Looks good. That volume should come out to be 125 over 3 cubic units. Now, what if we were to do cross sections, the same function of the parabola and the line x equals or y equals x plus 4, but instead of our cross sections being rectangles with height of 2, what if those cross sections were squares? Let's see what that looks like. Bam! I hope showing you step by step the construction of this three-dimensional solid allows you to see that I'm trying to show that it's lifting up and sort of out of the chalkboard, and maybe allow you to create similar drawings yourself. Okay, so we still have the same function, y is equal to x plus 4 and y is equal to x squared minus 2, defining the boundaries of our region, but each of these cross sections now, still cut perpendicular to the x-axis, are going to be in the shape of a square, as opposed to a rectangle where one of the measurements are fixed, and which makes it kind of a bit of a harder diagram to draw. But we have a square. I've taken this yellow cross section, tried to lay it down flat so you see it's not a rectangle. The length and width are both going to be defined by the distance between the functions, x plus 4 minus x squared minus 2. Yes, my mic is on. Okay, so kind of a big deal. Should have checked that before we started, right? The volume, therefore, is equal to the definite integral from negative 2 to the upper limit of 3. We found that in the previous example. It's the same functions again, just a different cross-sectional shape. And then we have negative x squared plus x plus 6, but this time squared. So instead of going through all the algebra step by step, because that's going to be a little bit tedious to square a trinomial, let's just let me step off and reveal the solution one step at a time. This will be very similar to the previous example. Bam! Well, that took a few tries, but I got the drawing done the best I can to represent the problem. Our last example. Find the volume of the solid whose base is bound by the circle x squared plus y squared is equal to 16. A circle whose center is at the origin and whose radius is equal to 4, of course, and has equilateral triangle cross sections that are again perpendicular to the x-axis. So we will need an equation, again, y in terms of x, and we're going to integrate with respect to x. Okay, so I've made a different orientation of my x and y axis again to try and give us the best representation of this graph that I can. And we are going to be looking at independent values of x to give us values of y. Well, as we started off the video, as long as you know the area of the cross-section, then you can find the volume of the solid. Well, the area of a triangle is 1/2 base times height. But if I'm going to integrate with respect to x, or having an equation y in terms of x, I need an equation that is in terms of only one variable, not two. So we need to look at our properties of equilateral triangles to see if we can't rewrite this. So we have an equilateral triangle, which of course is also equal angular, so each of those angles are equal to 60 degrees. We're going to identify these sides as a length of x, and so the area is going to be of an equilateral triangle 1/2 base, which is going to be our base identified with the value of x, times the height. So I need to figure out what the height is in terms of x. And we're going to do that with our properties of equilateral triangles and something we maybe haven't looked at too much since setting up the unit circle, 60-30 triangles. And we first saw those, of course, in geometry. When you take an altitude, of course, and you drop it down from a vertex of an equilateral triangle, or actually isosceles as well, you're going to cut the base in half. And that height is also going to not only be a bisector of the base, but with equilateral triangles, and if it's from the vertex of an isosceles triangle, you will also bisect this vertex angle up here at top. So this is 60 degrees, this is 30 degrees, and now remembering our ratios of 60-30 triangles, well, I've already got my hypotenuse labeled with a value of x, which means that the side opposite 30 degrees is going to be half the hypotenuse. Again, I'm looking at this perpendicular line coming down here from the altitude to the base, and that is going to be 1/2 x. Well, okay. And actually, let's just draw this out here too. When you have a 60-30 triangle, the base ratios, or the generic ratios, are 1 to square root of 3, or you could have seen that as 1x, 2x, and x square root of 3, or square root of 3x. So we have x, we have 1/2 x, which means the height of this triangle is the square root of 3 times 1/2 x, or the square root of 3 over 2x. So coming back over here, trying to develop our area formula, 1/2 base times height. And of course, 1/2 times square root of 3 over 2 is equal to square root of 3 over 4 x squared, and this is the area of an equilateral triangle, or A of x, our area formula in terms of x. So now I have enough information with my drawing and knowing the properties of equilateral triangles to write a definite integral with respect to x, or integrate with respect to x. Let's get this cleaned up and get that for you. So our volume comes out to be the definite integral from -4 to 4 of square root of 3 over 4 x squared dx. I came up with this area formula just sort of in general terms, and I called the side, I just picked a variable of x. I think it's a little misleading and a little bit confusing to write it that way now that I've written this and I've looked at my diagram. So I'm going to replace this x squared with a more, I think a bit more understandable notation of that it's the length of one of the sides of the equilateral triangle squared dx. And I want to rewrite that because, well, you know, this is supposed to be the formula for the area in terms of x. And while I showed you how to come up with and how to find the area of an equilateral triangle, I really didn't take any consideration to the equation of the circle, which is defining the base and obviously defining the length of the sides of these equilateral triangles. Let's just put that back into a general term of just, it's 3, again, square root of 3 over 4 times the length of the side squared. Now let's figure out a function that describes the length of a side. Well, again, I'm cutting my cross sections perpendicular to the x-axis. I'm integrating with respect to x, which means my function needs to be y in terms of x. Well, I got that sort of in terms for the area, but let's take a look at the equation of the circle. We have x squared plus y squared is equal to 16. Subtract both sides by x squared, and we get y squared is equal to 16 minus x squared. Square root both sides, and we get y is equal to plus or minus the square root of 16 minus x squared. And I need that plus or minus because as I choose my independent variables of x, I've got a sort of positive side of my circular base and my negative side of the circular base. So I need to account for that plus or minus, but I don't want to do 2 integrals, I want to do 1. And let's, of course, remember that as we drop these altitudes down on these equilateral triangles, we're bisecting the base. So I can look at just one of these roots and then multiply it by 2. And that would give me the entire length of the side. Length here, double it to get a length on the other side. And we get that the equation of our side is, don't forget that power of 2 there, 2 times the square root of 16 minus x squared dx. Now, taking care of this, we have the definite integral from negative 4 to 4 of square root of 3 over 4 times 4 times 16 minus x squared dx. And let's go ahead and close that parentheses because 2 squared is 4. The squaring is going to cancel out the square root symbol, and the multiplication of 4 and the division of 4 are going to themselves cancel out. So I'm going to step off and sort of clean this up a little bit more and give myself some room to finish up our problem and also finish this video. So we pulled that square root of 3 out front. Before, in an earlier problem, I distributed that constant through, but since that's a radical, I thought it easiest to pull it out front. The 16, integrating 16, we have 16x, and taking that power and increasing it by 1 and such, we get negative 1/3 x cubed. Finishing the definite integration process, we get a volume of this solid, which is equal to 256 square root of 3 over 3. I started to run out of there. Vroom cubic units. So that's the end of my last example and my video. I'm Mr. Tarrou. Go do your homework.